Hello and welcome. I'm Stephanie Hendrickson, Executive Editor with Additive Manufacturing Media, and it's my pleasure to welcome you to today's webinar brought to you by Fortify. So materials development has been one of these ongoing challenges in additive manufacturing. We need more material formulations, we need the print parameters to go with them, but sometimes the formulation capabilities can actually outstrip the software and the hardware that we have available, which slows down the introduction of new materials. So in today's presentation, we're going to hear how Fortify is aiming to solve this problem for advanced photopolymers that are used in digital light processing, or DLP. We'll hear about the technology that enables its Flux series of DLP printers, which can handle viscous and heavily filled resins, as well as the Flux Developer software toolkit for materials development. Our speaker today is Phil Lambert, the lead customer solutions engineer at Fortify. Phil is a mechanical engineer with almost a decade of professional 3D printing experience. So before I turn it over to Phil, just one or two housekeeping items. We will have time for questions and answers at the end of this session. So if you have questions at any point during the presentation, there is a Q&A panel, should be on the right side of your screen. Just type them in at any time and we'll go through as many as we can at the end here. And I also want to let you know that this webinar is being recorded. So if you can't stay for the whole thing or you want to reference it later, you will get a link to the recording after the fact. So with that, I will hand it over to you, Phil. Take it away.
Thanks, Stephanie. Good morning, everyone. Thanks, Stephanie, for the wonderful introduction. My name's Phil. I am, as Stephanie said, the lead customer solutions engineer at Fortify. And today we're going to be talking about digital light processing and how printing fiber-filled systems is a challenge and how Fortify tackles it. I'll talk briefly about some of the technologies on the printers themselves. I'll overview our materials configuration development software called Flux Developer, and then we'll walk through some use cases and how Fortify has leveraged these tools internally and with our partners to bring new high-performance photopolymers to market. So I also want to point out that in the sidebar over there is a poll. So at any point during the presentation, if you don't mind filling out that poll, that would be really awesome. So, all right, let's step into it. So I'm going to start with two statements just to scope this presentation a bit and scope the value proposition of Fortify. Statement one is that step change in photopolymer material performance properties calls for particles or fiber additives. So photopolymers have been in a space for a very long time where they're neat, where they're unfilled, because there's some serious processing challenges around filling photopolymers to get that next level of performance. And so that leads me to statement two. Fiber-filled photopolymers are typically very difficult to print. And so with those two statements in mind, let's talk about Fortify. So Fortify is a venture-backed 3D printing OEM. Up until this point, we've raised our Series B in the last, probably about a year ago now, $20 million. And we're located in Boston, Massachusetts, and we're a big group of 3D printing nerds and engineers working on developing this next generation of technology. The Fortify platform can be summarized by these three verticals: hardware, software, and materials. We've developed industrial-grade 3D printing systems and paired that with data-driven software and high-value materials to offer a full, holistic experience for our customers. The Fortify Flux, the Fortify family of 3D printers is called the Flux family. This is our introductory series of printers. We've got the Flux Core, the Flux One, and the Flux 3D. All three of these systems have the same build volume of 8 by 4.5 by 13 inches, with the same Z resolution capability from 35 to 150 microns, and the same pixel pitch at 75 microns. But they're different in how they engage with our fiber alignment Flux Print technology. I'll talk about Flux Print a bit, but just know that the Flux Core has no fiber alignment, and it just leverages our heating and mixing systems to print highly viscous fluids. The Flux One has Z alignment, so aligning fibers in the Z direction to help with anisotropic material properties introduced by layer-to-layer interfaces. And then the Flux 3D allows for three-dimensional, arbitrary, defined fiber alignment. We'll talk about that on a later slide. The other note I wanted to make is that all of these systems are capable of putting 2,000 newtons of plunge force through the material to achieve that next layer. And all of this combined allows us to process a much wider range of materials than has previously been able in industry. One of the things that all of our systems have in common is this ability to mix, heat, and circulate fiber-filled suspensions. We call this technology continuous kinetic mixing. CKM is the acronym we use. And what this allows us to do is take filled systems, circulate it through our internal CKM system, heat it, and mix it. And this enables us to keep all those fibers in suspension during the printing process so that your material is the same at the beginning of your print and at the end of your print, and there's no sedimentation that occurs. This is a schematic of how CKM works. On the right side here, there is an outlet port out of our print reservoir driven by a peristaltic pump. That pump leads into a mixer where the resin can be added during your print if you'd like. And then it's heated and mixed in this mixer and then distributed back into the print reservoir through an inline drip feed filter. And so all this happens on the machine. And leveraging our ability, some of the other technologies like our ability to put those 2,000 newtons of force through the build head, combined with CKM, expands our processing window, right? That's the title of this presentation, expanding the processing window of DLP 3D printing. And so with these technologies, you can see that on this lower left side of this chart here, on the y-axis, we have sedimentation rate. On the x-axis, we have viscosity. Other DLP printers play in this space that it's great for processing neat photopolymers. Neat photopolymers have done a great job in industry, but when our customers are looking for that next level of performance out of their machines and out of their printers, and out of their materials, they need to introduce these additives. And so we also are developing materials ourselves and with our partners. And on this chart, you'll see that we have this digital tooling resin, our low loss 2.8, and our low loss 4.9. Those are Radix materials from Rogers Corporation. We have higher degrees of viscosity, higher degrees of sedimentation rate because we're putting particles into these systems to modulate their performance. And as a result, we have to manage those higher degrees of sedimentation, those higher degrees of viscosity, and we do that with CKM and some of the other technologies on the 3D printers. Looking at CCAMs Advantage, you can see that on this chart, we are looking at density of the overall material system over time without CKM and with CKM. And so with this continuous kinetic mixing technology, the density of that system, the homogeneity or the suspension of that system remains consistent over a 48-hour period, where if CKM system was not running, particles settle out over time. And this is exhibited by these two parts 3D printed on the right here, the leftmost of pyramid in that right image was printed with CKM. You can see the visible homogeneity in this clear base material populated with a white fiber additive compared to the right side where very clearly the fibers have settled out of the system, and there's a difference between the density of the printed polymer on the first layer versus the last. And that is what CKM introduces in terms of stability of your material system and keeping those fibers suspended while you're printing. So now I'm going to talk about Flux Print. This is the technology that exists on the Flux 1 and the Flux 3D series of 3D printers. And this is fiber alignment. So we leverage electromagnets to align fibers. I'm going to play this video here. You can see that when we activate the electromagnets, those fibers align along the field of magnetic flux, and then we cure them into that location. And this is how it works. We identify areas that we want to align. We turn on our magnetic field. Every fiber in that reservoir will align in the orientation of that magnetic field. And we lock in only the voxels that we want to lock into that fiber orientation by curing those voxels with UV light. Once we've done that, we can shift the field, and we're still on the same layer now, but we're shifting the magnetic field to align every other unpolymerized fiber into a new orientation. We can then use the UV light, again, to lock in those newly aligned voxels. And then we can repeat that process for every voxel or every region of voxels within your layer that needs a unique fiber alignment. At that point, we peel and we move on to the next layer. And so that brings me to Flux Developer. So I've just introduced the core of the technologies that Fortify offers for printing. And now Flux Developer is a tool set that allows our customers to leverage those capabilities to enable fiber-filled systems, to enable that next level of performance out of your DLP 3D printer by using the same tool sets that our internal process engineers and material scientists use to do their formulation. In fact, that's where the genesis of this entire product came from. How do we get these tools into the hands of our customers to allow them to do really interesting materials development? So Flux Developer, in a sentence, is a software product that enables new materials development for the Fortify Flux series of 3D printers. The Flux Developer product can be described in 4 elements. The first being Flux Portal, which is a browser-based web app, and I'll talk about that in much more detail in following slides. Flux Host, which is the on-machine user interface. We've got some built-in experimentation that users can engage with on Flux Host. We have Compass on the bottom left here. This is our build preparation software. I'm not going to be talking much about that today, but it integrates with Flux Developer because this is where you design your build, select your layer thickness, slice, and create your build file. And on the bottom right here, we have a series of recommended experimentation that happens off the machine that'll help you as a user of Flux Developer find success more quickly. And so we offer support and recommendations for some of these off-machine experiments. So Flux Developer has a workflow that we recommend, and it's here. There's a series of feedback loops. Typically, when someone's engaging with this tool, they have a materials formulation in mind. They're thinking about maybe they want to improve, the stiffness or the toughness or the thermal conductivity or electrical conductivity, right? They have some goal for their materials formulation. So it starts there. Now, the next step is moving on to Flux Host. You're thinking about doing some onboarding experiments. And these onboarding experiments include photokinetics analysis, build plate adhesion, sedimentation rate analysis, rheology. And after you've done those onboarding experiments, customers tend to move on to materials characterization, materials profile creation. So this happens in Flux Portal. This is where folks can sign into a web app and start defining what those material parameters, material print profile parameters need to be, and then push those material configurations to the printer. And so I'll also, like I said, I'll talk much more about Flux Portal. It's a big part of our product. But in order to better understand how all of this interplays, how do you go about selecting certain parameter sets to improve certain parts of your print process, I like to introduce the anatomy of a layer. So it has these 5 steps, and we'll start with plunge, right? Plunge is the build plate moving into the reservoir through that presumably thick viscous fluid. And during that plunge step, one of the most important things we think about here is resin rheology. How is that resin going to flow out from beneath that build plate as we're compressing it and squeezing it between a rigid piece of glass, that's that blue rectangle there, and the build plate. And within that step, we have control over things like the plunge speed, the plunge acceleration, the plunge force threshold to get that plunge step tuned. And then after the plunge is complete, we move on to alignment. This is where we are aligning all of those fibers in that suspension. Things that we're interested in about the resin is the magnetic susceptibility of those fibers to alignment. And then again, rheology, right? Because those fibers are having to turn and align within a bath of resin that may be very thick. And so the period of time, the alignment time, and that alignment vector, those are all functions of magnetic susceptibility of those particles, and also resin rheology. After we've completed our alignment, we move on to UV exposure. This is when we're turning on the projector and we're curing our shapes. And the important part about this step is photokinetics. How does this material respond to UV light? How does it respond to UV intensity and UV dose? How much time do I need to spend exposing? Do I need to be concerned about my intensity? After the exposure is complete, we move on to the peel. Again, resin rheology playing a big role here. How is that resin going to flow back into that gap left behind by the build plate in the part as it peels off of our film that sits right in between the glass and the resin? And also playing a role here is your resin green body strength. If you aren't doing a complete cure in the 3D printer, then you have to be concerned with how strong your parts are. Are those parts strong enough to survive the peel? And are there ways that you can reduce the amount of force being experienced by the parts when they're getting peeled? And so in this step, we have control over things like layer height, peel acceleration, peel height, peel speed. And then once your peel is complete, there's often every 5 layers, every 10 layers, a wipe step. And this is our wiper that moves across the film and helps to resuspend some of those particles. And so things that are important during this wipe step we have to think about is our sedimentation rate. And again, rheology plays a role here too. And so the reason I bring all this up is because these are the types of things you can control in Flux Portal. And so on the top here in this materials configuration creations interface, we can see on the left image here a series of created materials configs, their names created by, and their status. If they're active, they're on the machine. If they're retired, they just live in this library. And on the right image, on the top rightmost image, we can see how someone could go in and edit or modify some of these peel settings. And that's what the screenshot is, just peel. But if you look at that top across the top, you can see we have CCAM settings, plunge settings, and UV settings as well. So when you've conducted your experimentation and you are ready to create materials configuration, it's in this Flux Portal that you'll have access to do that. But Flux Portal also does more than that. It has your print status, your print history, and analytics related to every experiment and every print that you've run. And this allows you to track your success of your experiments, track your experimental variables across your different builds. It allows you to define whether or not you had a success or a failure on each build, duration of print, material consumed. There's a whole bunch of stuff that's tracked, and it applies a unique ID to every print you've run so that you have complete history over every single experiment you've run. So these two things together live on Flux Portal. Great. We have Flux Portal. Now we need to decide how we're going to define which each of these parameters need to be. And we do that through a series of experimentation. And so like I mentioned earlier, we've got the off-machine experiments and the on-machine experiments. The off-machine experiments are here to help us understand the rheology of our material and the sedimentation of our material. And the on-machine experiments are primarily designed right now to help us understand the cure kinetics and the build plate adhesion. And we'll walk through each of these tests. But on this slide, I do want to emphasize that this is only the first part of a growing catalog of experiments that Flux developers will have access to, right? We're always going through and defining new experiments internally in our material scientists and process engineers to help us better understand and improve our printing processes. And as those internal capabilities grow and mature, they get productized and moved into Flux Developer so that our customers will have access to those as well. I have a slide at the end that talks a little bit about product roadmap for Flux Developer. So I'll touch on some of those details later. So starting off with our off-machine experimentation, in that anatomy of a layer, the one thing I said the most was rheology. So rheology, for those who don't know, is the study of flow and deformation of a fluid. That's a pretty simple way to describe rheology, but we'll leave it at that for today's webinar. And out of that, I want to highlight that viscosity is a critical metric for us. If you're looking at this this chart on the left, we have viscosity on the y-axis, shear rate on the x-axis. And what we're doing is we're plotting the viscosity of a filled fiber system as a function of shear rate and as a function of temperature. And you can see that the material's behavior changes as a function of shear rate at different temperatures. And so that means that there are process inputs that can control how this material's behavior changes. I'm talking specifically about CCAMs resin temperature and shear rate. And shear rate can be controlled through, build plate plunge, for example. But viscosity and the rheology of the system is also a function of your material formulation. What is the base resin viscosity? What is your fiber content? What is your fiber morphology? What is your fiber density? What is your particle size distribution between your different sizes of particles within your resin? All of these things contribute to your rheology, and as a result, contribute to the printability of your system. Off machine, we also evaluate particle sedimentation. So sedimentation describes the rate at which a fiber falls out of suspension. There are some systems in which this happens at a much faster rate, and some systems in which this happens at a much slower rate. We provide this velocity calculator, which helps our customers do a first-order approximation of sedimentation in our system. And this, it allows you to understand it as a function of some period of time in the system of critical idleness. Maybe it's the time in between wipes, or maybe you're peeling very slowly and the system is remaining idle during those slow peels. And so you're able to use this calculator to evaluate how this particle might settle during those critical periods of time. We also can support and provide insight for users who want to run practical experiments, right? Sedimentation is a pretty easy thing to study. You put your suspension in a beaker and evaluate sedimentation versus time. And you can cross-compare across different systems for particle stability. And so off-machine particle sedimentation is something we hope our customers will consider as they're going through resin formulation. But moving on to the machine, and when I mean on machine, I mean in the user interface of FluxHost, we have something we call the slot working curve. And slot working curve is a customizable experiment that explores the critical relationship between UV energy and the resin photokinetics. And what folks have access to in this tool set is the ability to customize how much energy goes into your depth of cure sample, your slot working curve sample, at what intensity. So that creates this array of 24 samples. After you just press one button and the machine cycles through a series of 24 exposures at different intensities and creates these samples. And these samples can be used to evaluate both the depth of cure of your system, but also scatter, right? Every particle filled system introduces some degree of photon scatter. As that UV light enters into that system, it's going to interact with those particles. The particles are going to block that path of light and cause it to go somewhere else. So evaluating scatter is also a very critical part of this experiment. So thinking about depth of cure, I've got some real data here on the left. I've obscured the actual dosages for confidentiality reasons, but it shows you there's a dependency on our depth of cure as a function of dose. And that slope of that chart changes as we get to higher energies and as we start to reach that plateau where we can't achieve any greater depth of cure. But if you look at this chart and you look on the y-axis, and our depth of cure is measured in millimeters here, we're measuring up to 700 microns in this experiment. When in reality, we're probably more interested in printing at layer thicknesses of 50 to 100 microns, maybe a little bit larger, or maybe even a little bit smaller. And so that area around that first dosage is where I want to learn more. And so after you run this first screening experiment and you understand how your material behaves over a large range of dosages, you can run another experiment, really shrink that range down and study dosages just below our first dosage here, or just above, so we can really tune and better understand how this resin system responds to the input dosage. But also, as I was saying, we can use these little samples, these little slot working curve samples, to understand photon scatter. And what you're looking at on this chart on the x-axis is dosage, 1, 2, 3, 4, 5, 6, the same dosages as before. And then within each of these little regions here, we're looking at intensity. So we're looking at different intensities. And we are measuring the width of one slot on this sample. And that width has a nominal width of 975 microns. And each of these dots on this chart represents a deviation of some degree from our nominal width. As the width shrinks, we are getting overcure in these slots. And so we're understanding now that there's a relationship between the amount of energy we put into this system to get to your depth of cure, but also it's a function of scatter. That the scatter is a function of the energy and the intensity as well. And so we measure this using a microscope, and we look at it under a high degree of magnification to really understand what that looks like. But we also have these tools that our microscope has, and maybe your microscope has it too, to evaluate the 2D profile of these slots. So getting the information that we're getting beyond the width here is also what that wall looks like within that one layer. Are we experiencing a lot of Gaussian blur and we're getting non-straight walls, or are we getting really nice crisp walls? And so this is another way that you can use this sample to evaluate and understand your scatter behavior. And so this slot working curve is used by us to really understand the photokinetics of our system, especially with respect to resin formulation. So users should consider how to use their slot working curve result and how it relates to their system formulation. So there are a variety of things in formulation that can impact your depth of cure and your scatter. I'm talking about things like your photo initiator selection and photo initiator volume percent content, particle color, morphology, fiber alignment, content of your particle in your system. And then there are things like inks and dyes and other light management agents that you can consider to help to tune as you run through this screening slot working curve experiment to help to tune the behavior of your system in a print environment. So moving on from slot working curve and photokinetics, we have another on-machine experiment called build plate adhesion. This is a pretty simple experiment where we offer the flexibility to customize the energy that goes into the first layer of every build. And that goes through a series, we can customize across a series of columns here. So you have 6 entry dosages that relate to these 6 columns of sample generation here. And so this helps us to understand how much energy we need to put into the first layer to get stuff to stick, but also not so much energy that we can't get it off the build plate, because that is also a problem on some occasions as well. So we're looking for a sweet spot here. Turns out that our customers who already have Flux Developer in the field tend to use this build as their first print of a new resin system. It's already on the machine. It's easy to set up. It's easy to run. So it serves as a great first print for a new system as well. Okay, so I walked through all the tools that are available in Flux Developer, and now I think a great thing to do is walk through an internal case study. How does Fortify think about formulation as it relates to Flux Developer, and how do we leverage these tools internally to do our own materials development? So we're going to start talking about our thermally conductive dielectric. So we had customers who had interest and a goal for us to create an electrically insulative, thermally conductive polymer dielectric. And those target requirements, like the critical metric, right, we're designing around here is material behavior in the application, the material property in the application. But as a secondary point of development, we also want to make it printable. We want to get to feature sizes that are suitable for our application. And the example I'm presenting here, that might be heat sinks for electronic applications. And also we wanted to have a high degree of productivity suitable for production applications. So that means that we're thinking about, and we're focusing on optimizing around the material behavior in the application, but also thinking about making it a material that makes sense for production. So that means economics around throughput, et cetera. And so if you look at this chart on the right, we have thermal conductivity on the x-axis, electrical resistivity on the y-axis, and we're looking for something that has a high degree of electrical resistivity and as high of a thermal conductivity as we can achieve, targeting 2 milliwatts. As a point of comparison, neat photopolymers tend to have a thermal conductivity of about 0.3 watt per meter Kelvin. So we're looking for a 10x order of magnitude improvement. And when starting off a resin formulation, we had to select a method of transporting heat efficiently through the part. And we decided on phononic conduction. And so in a typical system, if you look at this chart in the bottom left here, as our volume fractions of these solids that we are putting into the system increase, we're going to see a decrease in depth of cure. But at the same time, we're going to see an increase in viscosity, which is a challenge, right? A decrease in depth of cure and an increase in viscosity make for hard printing challenges. But at the same time, our critical metric here that we're optimizing around, our thermal conductivity, is increasing, right? So at some point, we're going to experience the onset of percolation. And when percolation occurs, that's when we're going to see an increase in thermal conductivity. So thinking about this materials formulation at a high level, adding more particles can increase our conductivity, right? That's the thing we want to optimize around. But more particles also increases viscosity, changes our rheology. More particles also decreases our depth of cure. So there's going to be a sweet spot on there, somewhere in there where we'll be able to nail our conductivity and also achieve a degree of viscosity and depth of cure that allows us to print nice parts. So thinking about this from our phase 1 DOE, right? This is real data for as we were walking through the development at the first stage, like our first screening experiments for this material. We have to consider the volume percent of our additive versus conductivity. I do want to highlight here that we're looking at liquid conductivity on the left. That allowed us to really optimize our time to characterization here. But the actual metric in the application is bulk conductivity of the solid. So there's a difference there, but it allows us to do some real screening experiments. All right, so looking at this chart in the middle here, volume percent filler versus conductivity, we can see that at any degree of volume fraction of particle A, particle B, or a combination of particle A and B, we're getting increases in thermal conductivity in the liquid state. But on the other hand, as we increase these filler contents, we're getting significant increases in viscosity, especially for particle A, right? We're getting high viscosity at lower volume fractions. Particle B, we're seeing slightly better behaviors, but turns out if you combine particle A and particle B in some concentration, we're able to get to higher volume fractions, which leads to higher conductivity, but at lower viscosity. So there's an interesting synergistic interaction happening between particle A and particle B, allowing us to get to the viscosity that we want without a significant unmanageable increase, thermal conductivity that we want without a significant unmanageable increase in viscosity. So great. And that led us to our material. And I just want to highlight throughout that whole process, that whole screening, design formulation process, we're always probing for the photokinetics. We're always running those slot working curves and build plate adhesion tests, making sure that the formulation we're dealing with, besides having a manageable viscosity and a desirable thermal conductivity, is also able to achieve the depth of cure and the scatter behavior that we need to meet our application requirements. And again, as I said earlier, in this case, it's products like electronics heat sinks and cold plates. And so we were able to design a system that had a nearly 2 watt per meter Kelvin thermal conductivity, while also having dielectric strength of over 27 kilovolts per millimeter. And here's an example of those printed parts. So we get the heat sink on the left here. We've seen that picture a few times. And we're also have printed some cold plates. The cold plates are you might find in server rooms managing the heat generated from servers. Okay, so that's how Fortify has leveraged Flux Developer to do materials development. But our partners have done so too. So we have 2 material partners that I'm going to talk about today, Rogers Corporation and Tethon 3D, who we partnered with to bring new materials to market. First one I'm going to talk about is Radix. Radix is a 3D printable, low loss printable dielectric photopolymer. This is used, this has a dielectric constant of 2.8 with a loss tangent of 0043. It's fiber filled, right? And as in the fibers, the additives in this system are used to tune that dielectric constant, and it helps to improve the loss tangent. So this system relies on CCAM and the other technologies in the Flux printer to print these grin lenses. And the grin lens is the application of that I'm highlighting on this slide. It's a gradient refractive index lens used in RF beam forming and beam steering applications, right? It's a lens for RF energy. And this lens helps our customers in the application to increase the aperture efficiency of antenna systems, the gain of antenna systems, and offer and introduce greater flexibility in beam steering. These are the types of things that applications in the markets of 5G, radar, defense and aerospace are all looking for solutions like this. So beyond that, Fortify also partnered with Tethon 3D. And Tethon 3D is a leading developer of photopolymer ceramics. So these are ceramics that are loaded to a very high volume percent. Sorry, these are photopolymers loaded to a very high volume percent of pure ceramic additives, which then go into a sintering furnace, burn out the polymer to create fully dense ceramics. So that means these 3D printed ceramics have excellent thermal conductivity, for example, especially in this alumina heatsink example, and have an excellent sinter density and an excellent operating temperature, nearly up to 1700 C. And so these two examples, both Rogers and Tethon 3D, have leveraged all of the entire offering in the Flux Developer toolkit to develop and onboard these systems onto a Flux Core 3D printer. But there's more to come, right? I talked about the roadmap for Flux Developer earlier. We are constantly developing those experiments in-house, and we want to push those experiments for onboarding new systems out to our customers. And we've already roadmapped some of these. The first one I want to highlight is that we're going to improve that slot working curve test. It's already very powerful, but we want to give it more flexibility. We want our customers to be able to evaluate the photokinetics as a function of magnetic flux and alignment. We want them to be able to understand how temperature plays a role in the photokinetics, and also introduce geometry customization. So you're not stuck with that slot working curve if you don't want to use it. That'll always be there, but you'll have the opportunity to customize those sample geometries. And all that flexibility will build into the slot working curve and build plate adhesion tests. Also, we understand that the film that sits in our system may not be the right film for your material system. So we're going to have a series of offerings of different types of films that you'll be able to evaluate in an on-machine test to understand how peeling and plunging onto this film using your material system will impact the lifetime of that film. Is it getting foggy? Is it getting scratched? Is it getting dented? And so we'll have some offerings there for folks to be able to understand the interaction between the film and the material. And then we understand that rheology. I talked so much about rheology today. But to understand rheology, you need a pretty expensive lab tool. Not everybody has that. So we're working really hard to bring a version of rheology characterization onto the printer. We got some really interesting technology there. We're really looking forward to building that out. I think that's going to offer a real high degree of flexibility to our customers. And then these last two at the end, we're looking at surface roughness as a function of our input parameters, right? Surface roughness is critical in so many applications across 3D printing, but it's a hard thing to optimize. And it's a challenge to optimize because you have to run test after test of different parameter sets, different layer thicknesses, different exposures, different peels, different plunges to really understand how to best optimize this material system for surface roughness. And we have this really cool tower test that runs through a series of parameters in one print. If you just look at different regions along that tower, you can really start to understand how surface roughness is impacted by those parameters that you've selected. And then finally, the last but not least, I mean, we've got so much more coming, but these are the ones that I put on the slide, is variable intensity and dose dog bone experiments. We talked about green body strength, and this speaks directly to that. Looking at green body strength as a function of input intensity, as a function of input energy dosage for every layer. So this is just a small portion of what we have planned for Flux Developer. We're also going to build out Flux Portal. And as we start to understand more about what plays a role in these really complex material systems, more parameters and different parameters will be added into the material configuration tool set to enable our customers to print even better. Okay, last slide, partnerships. So Fortify partners with a variety of academic institutions, national labs, materials companies, enterprise R&D labs, and we're looking for partners. So reach out if you have a great idea and you want to discuss partnership opportunities. Cool. All right, that's it. Thank you so much for listening. My name, again, is Phil Lambert. I am the lead customer solutions engineer. My charter is to help people use this equipment and do cool stuff. I'm looking forward to helping you do that. My email is here, phillambert@3dfortify.com. Thank you so much.
All right, thank you, Phil. So we do have some Q&A to get through. Before we do that, I want to direct everybody to the poll once more. If you have not responded yet, please take a moment, hop over to that tab that says polls and just answer that question. And we'll get into the Q&A, and you can keep submitting questions as we start going into these. So here's one right off the bat. What type of fibers are able to be magnetically aligned, and are there specific sources for those types of fibers?
Oh, yeah, that's a really, really nice question. Um, so we can align ceramic fibers. All it takes is you have to tag those fibers with magnetically alignable nanoparticles. And we can support you in understanding how to do that process. But in generally, anything that responds to an electromagnet, right? Anything ferrous. Um, so stainless steel particles, anything that can be moved using an electromagnet can be aligned. There are sources out there for fibers. Sourcing is something we can also help you with if you're looking for something specific. Maybe we have experience with it already. But yeah, generally, to answer that question at a high level, anything that can respond to a magnet can be aligned. It's really hard to align spheres. So if your particles are spherical, you can't align it. So you need a particle with some degree of an aspect ratio in order to be able to align it.
Got it. What is the upper viscosity limit for your system?
Another great question. There are several ways to answer that. We have processed materials as high in viscosity as 10,000 centipoise, and I think in some cases we've done quite a bit higher than that. To be able to circulate it is a different question, right? So we can print using CCAM to heat and mix, but in order to be able to do that, you need to be able to have it to flow at room temperature. You can preheat your resins and get it into the system, but you run into some risks of the resin cooling in the lines, and then you have a big cleaning problem on your hand. But in general, like 10,000 centipoise and above is possible on our systems. It just depends on a few specific, criteria. Beyond that, right? Viscosity, as I talked about, isn't the only metric of rheology that plays a role here. There's a shear thinning aspect to your resin. We can even go to higher room temperature viscosities, and by introducing shear, we can leverage that behavior to 3D print that material. So I'm sorry that wasn't a fully straight answer, but there are some nuances to that question that I wanted to touch on. So thank you for the question.
Would there ever be a case where you would use like Flux Developer and some of these tools in developing a non-filled resin, just like a neat photopolymer?
Sure, absolutely. All of these tool sets work just fine on neat systems, right? As my manager likes to say, at the end of the day, this is just a really, really good DLP printer. And so all of those tool sets, the slot working curve, the build plate adhesion, the rheology, all of those things can be leveraged to develop unfilled systems. It just turns out that the system's also designed to process filled systems as well. So that's where we see the value prop. If you want to do neat systems, it's available to you as well.
Can you talk about other materials that you've developed internally using the Flux Developer toolset?
Yeah, all of our materials. We got another material that's we've been printing for a few years now called digital tooling resin. That's a material that's filled with a small volume percentage of an additive that we leverage to do alignment for our injection mold tooling applications. And we've designed that system. That system, I should say, has a very high heat deflection temperature and a very high strength and high stiffness, the types of things we need for injection mold tooling. And so that's one system we developed on Flux Developer. Another system is our ESD resin. So it's another resin filled with an electric dissipative additive. And so we're reaching a degree of conductivity that doesn't transport, doesn't use for conductive traces, for example, but helps with electrostatic dissipation. And we filled that with some metallic elements to facilitate that ESD behavior. those two systems, besides the thermally conductive material, and all of our partner materials were developed on Flux Developer. It's used, as I said, and it's not an exaggeration, it's used every day internally at Fortify.
Is there an offline version of Flux Developer?
Oh, great question. We have a series of offline customers already leveraging this tool. We see a lot of benefit in materials development in some of these highly top secret lab environments. And so we worked really hard to make sure that many of these tools, unfortunately not all of them yet, but many of them are available in an offline environment, separated from the internet. Unfortunately, do make some small sacrifices, but they're there and you can use them.
So question is, can you print bigger stuff? And maybe just for context, like what is sort of your typical build volume?
Yeah. So the build volume is 8 inches by 4.5 inches by 13 inches, right? So the 13 inches is very large. And the question is, can we print bigger stuff? Yes. When we think about grin lenses, there's an interesting behavior where the lenses get large as a function of wavelength. And so when we want to print larger lenses for lower wavelengths, we have to get really big in our lens size. And what we've explored is the ability to bisect these lenses digitally and then assemble them together in a secondary step. So that's how we're managing that now. But we do have roadmapped 2 larger systems. One's called the Flux Core Plus, which is going to have a larger build plate and I think the same as the Axis. And then much further down the line, we're scoping out in our roadmap about 5 years probably of an XL system where the build plate is going to be 1 foot by 1 foot. So we're going to be able to print much bigger things in short order.
Nice. Okay, so we have a question here. It's sort of a 2-part question. So they're asking any capability with glass microspheres. We talked already about the difficulty with aligning spheres.
Mm-hmm.
So glass microspheres, is that possible? And then how about density gradient control across a 3D matrix?
Okay, I understand the first question. I think I will maybe have to discuss the second question a little bit. Glass fibers, spherical glass fibers. That was the question, Stephanie?
Glass microspheres is how they work.
Glass microspheres. Yeah. So have we had any experience with it? Yes, we have had experience with it. There's some interesting applications you can leverage it for, especially if those glass spheres are hollow. It's a ceramic. Glass is in the ceramics family after all. There's no reason that we can't print it. Yeah, sure. And I guess the second part was the gradient density across a 3D matrix.
Yeah.
So I think they're asking about the geometry of a matrix. Is that how you interpret it too?
Yeah, that's kind of how I.
Okay. Yeah. So the GRIN devices are a great example of that, right? The gradient refractive index is driven by localized density of the 3D printed material, which is when you want to control local density in a lattice, you control it by controlling your wall thickness of that lattice or the strut thickness of that lattice. So in one of our primary application spaces that we're focusing a lot and doing a lot of development on, we intentionally leverage a gradient of density by leveraging a gradient of wall thickness from the center of a lens to the surface of a lens. So we can physically introduce these gradient structures through geometry control, through how we expose our UV light into every layer.
All right. So one of the examples that you talked about was the alumina material, which is getting printed and then needs a sintering process afterwards. Does that change? Does that add additional experiments, or does that change the process of using the Flux Developer toolset?
Yeah, that's a really good question too. Sintering is a really hard part of this problem. Our partners at Tethon have introduced a sintering step as part of their Flux Developer workflow. We don't support it directly right now. It's not something that's built into the product holistically, I should say. But understanding what your part looks like as it comes out of the printer, and then the result you get after sintering is something that they've had to think very critically about when leveraging Flux Developer to optimize their printing, right? When you're not dealing with sintering, your end part is the part that comes off the printer. When you introduce the sintering step, how you cure the part, what the surface finish looks like, what those support structures look like, what your resolution is, what the tolerance you have is all a function of how that part changes when it goes into the sintering furnace. And so, yes, it has to be included into your DOE for your Flux Developer workflows. And if you have questions, more questions about that, happy to have a conversation around it if someone has a goal for developing some ceramic materials.
Awesome. All right. So that is the end of the submitted questions. I guess I'll give a few minutes here just in case anybody wants to jump back in. I do want to say, like, if you submitted a question and we didn't get to it, everything submitted has been recorded, and Fortify can follow up with you offline as well. So thank you so much, Phil, and thank you, Fortify, for making this presentation possible. Thank you to everybody listening in as well. The recording will be available pretty soon here after this concludes. You'll get a link to it in your email. And I want to just let everyone know we have an upcoming webinar on March 7th, which will be all about reverse engineering. So you can find all the details about that one on additivemanufacturing.media. Phil, thanks again, and everybody enjoy the rest of your day.
Thanks, Stephanie.